Hi, everyone. Today, let's do things a little bit differently. No new information. Let's review. Let's review some other things. Let's get ready for the next test. So on Canvas, we have the review sheet, the sample exam. Now, as it says right here in the middle, the actual exam will be shorter and will provide more spaces for your answers. And if you already do the sample test a couple times and you feel like you're just memorizing the answers, you're not really testing your ability to answer these questions, then you should go back and do some homework problems. Says HBA and quizzes, we don't really have a bunch of those. Although, can you take the quizzes again? I know you can take them a few extra times. Maybe the homework problem would be better. Although your first opportunity to practice for the exam is to do this sample test. And so I thought I would just pick out some of the key reactions and problems here and show you how I solve them. I don't have time to do all of these questions, right? But there's several types. First one is give the reagents. Second one is draw the products, and oftentimes circle the major products. That's going to rely on your knowledge of Zaitsev's rule, right? The most substituted alkene, carbon-carbon double bond, the most substituted alkene is the more stable product, and nature's favorite, that'll be the major product. Let's see, more drawing the products. Writing mechanisms. So using your curved arrows to show the correct order that old bonds are broken and new bonds are made. And then there's some multiple choice type questions to give you a feel for that, because I might format some of these questions in a multiple choice format. But most of them will be show your work and then upload your PDF of the work you've done. And then of course, we'll do some multi-step synthesis. More kind of short answer. Here's some homework questions. I thought I'll put them on the sample test so you realize, hey, when I write the exam, I might just go and reuse some homework problems. And then we got some more, give the reagents and naming and so forth. So yeah, there's a lot here to practice. Don't feel obligated to do the whole thing, but of course, the more you practice, the better prepared you'll be. So let's do a few of these and get a feel of how to get ready for the exam. Okay, let's start by giving the reagents. Scroll over a little bit. There we go, got some room now. Okay, so we have the starting material over here. We got the product over there, and we're supposed to give the reagents, the reactants, that allow this molecule to change into that one. And what is helpful is identifying what is common between the two. And so those are the atoms that are all the same from the starting material to the product. The only thing that's changing is an OH group. It's becoming a bromine. In fact, it's being substituted. So you might be thinking maybe SN1 or SN2. That could be helpful. On the other hand, SN1, SN2 has to do with halides leaving. And this is an alcohol. So it's probably not the right answer. Again, you're kind of looking for some clues here. Here's another idea. This bromine was not in the starting material. So your reagent has to supply the bromine. So that's a helpful hint. And it turns out that this alcohol is tertiary, right? So talk to the alcohol, say, hey, what degree are you? It's shy. So you have to go back to the carbon, ask the carbon, what degree are you? And it's this carbon is attached to 1, 2, 3 carbons, making a tertiary carbon and a tertiary alcohol. And it turns out tertiary alcohols react with HBr. The H combines with the alcohol, leaves, forming water. And it turns out this is a SN1 reaction, making water a good leaving group. And then bromine substitutes the place where the bromine used to be, or where the alcohol used to be. So there's the answer, HBr. How about the next one? Well, the only thing that changes is this chlorine became, well, what's the element D? Go to the periodic table, there's no letter D on there. No, this is hydrogen with mass number 2. That's deuterium. It is a hydrogen atom, but it has a neutron in it because 99% of hydrogen does not have a neutron. It's called deuterium, one of the isotopes of hydrogen. So the reagent has to supply the deuterium atom, and somehow the chlorine's got to get out of the way. We don't have any SN1 or SN2 reactions that supply a hydrogen atom. Instead, this is the Grignard reaction. So again, memorizing reactions. I forget the exact example that we provided in the video, but if you take magnesium, Mg, and a halide, primary, secondary, tertiary, attached to a benzene ring, attached to a carbon-carbon double bond, doesn't matter, it all works. You make a Grignard reagent, MgBr or MgI, MgCl, whatever the halide is, and then you can treat it with water or some other acid. That's a weak acid. Well, the Grignard's a powerful base, so anything that has a hydrogen on it, sorry, not carbon, not a CH bond, but pretty much anything else like ammonia. There's an H here, the nitrogen will let go of that hydrogen with this very powerful base, and you can put the hydrogen there. So the key is, instead of using normal hydrogen, use deuterium in your water molecule. So first step is mix in magnesium. So you can put a little 1 here saying, hey, reaction number 1 is first add magnesium, let it react to form the Grignard. And then step 2, add some deuterated water, D2O. And it does this sequence of steps, but on this molecule. Cool. Next one here, we're changing an alcohol to a chlorine. So hey, isn't that the same as alcohol to bromine? We just use HCl? And the answer is, that'll give you partial credit. Because this is secondary. In 1 or 2 of the videos, we talked about how the reaction runs through an SN1 mechanism, which creates carbocations. So in the mechanism, H plus goes on to the alcohol, makes water. Water leaves and makes a secondary carbocation. Darn it, tertiary carbocations are the most stable, or at least stable enough that they don't rearrange. Secondary can rearrange though. And guess what, right next door, there's a tertiary center. So we're gonna get a hydride shift and get a mixture of products. So HCl will make some of this, but also make some of the rearranged product. Actually, this molecule down here. So you don't want to use that. Instead, you want to use SOCl2. That's the correct answer. They'll take any degree, primary, secondary, or tertiary, change the alcohol into a chlorine. In fact, another answer that gives you full credit is to use PBr3 up here, because that takes an alcohol, primary, secondary, tertiary, and make it into an alkyl halide, a bromide rather, with PBr3. Now this one is tertiary and a tertiary alcohol. So yes, this one's okay. This gives you full credit, or SOCl2 gives you full credit. You don't have to list both, just give me one. Nice. Okay, let's do some questions for number 2 about predicting products, and then circle the major product. Okay, so what we got here, we have an alkene and we have a bromine. So those are the 2 functional groups in the starting material. And then what is that? And what is this? They kind of look the same, just a K becoming an H. If the reagents don't look familiar, like hopefully SOCl2 looks familiar. It's one of the reactions, one of the reagents we actually talked about in a video. We've seen it in the homework. This one actually showed up in the homework a couple times, but we didn't explicitly list it as a reagent to memorize. No. So if things don't look familiar, like if you look down here, this is less familiar. It's like we never talked about two carbons attached to a sulfur attached to sodium. We haven't seen that specific reagent. It was one that we did not have to memorize. Anytime you see something like that unfamiliar, start thinking SN1, SN2, E1, E2. That's what's actually happening for both of these. Okay, so what we got up here, let's start with the alkyl halide. This is secondary. That doesn't help. It could be SN1, it could be E1, it could be SN2, and it could be E2. It could be any of those. So then look at these and decide, well, which one's the base or nucleophile and which one's the solvent? The more reactive compound is the reagent. It's going to be either a nucleophile or a base, and this one has charge, and this one's neutral. That makes this one the solvent. We got a negative oxygen up here, just like NaOH has a negative oxygen. That makes this a strong base. Oh, and there's no resonance. So in the acetate anion, that oxygen is also negative, but it's resonance stabilized. And if you get resonance stabilization, stabilized means it's not very reactive, which means it's not going to be a strong base. It's more stable. It's calmer. It's less basic. That makes this a weak base. So as we start to look at, hey, what makes a strong base and what makes a weak base? Two ideas to think about. Strong bases have negative carbon, negative nitrogen, a negative oxygen. And if you want strong, don't have resonance. Next to the negatively charged atom, C, N, or O, next door to that, you don't want a double bond, whether it's a carbon to oxygen, carbon nitrogen, carbon carbon double bond. That will make it resonance stabilized and it will weaken it. Cool. All right, this is strong base, so that's favoring E2. Remember, E1 likes weak bases. The S reactions, SN1, SN2, want to substitute with a nucleophile. So what makes a good nucleophile? Strong bases and sulfur nitrogen. Strong bases and SN2, sulfur nitrogen, SN. Whoa, this is a strong base. So it's also a good nucleophile. So based on just the molecule here, we're thinking that could be E2 or SN2. Tiebreakers down here, the solvent. What kind of solvent is it? Is it protic or aprotic? Well, if it can hydrogen bond, it's protic. And there's the OH group. It's protic. It can make a hydrogen bond. And back in general chemistry, hopefully you learned that a molecule can make hydrogen bonds if it has an HF, an HO, or an HN bond somewhere in the molecule. And there is an OH bond right there, an HO bond. So this molecule can hydrogen bond. What does that mean? That's going to make SN2 slower. And the fastest mechanism wins. So top molecule says, yeah, SN2 is fine, or E2, I don't care. The solvent says, we're going to slow down the SN2. So that means the reaction goes by E2. What is E2? The E1 and E2 make alkenes and alkynes, double bonds and triple bonds. Depends on how many halides there are. If you only have one halide, then you get one pi bond, a double bond. And then where can it go? Well, in E2, you always start the double bond at the halide. So take away the halide. So start drawing the product over here. Copy everything over. The halide used to be here. So make sure you erase the bond and the halide. And then you can either make the double bond to the left, or you can go to the right. And then you can also get cis and trans isomers. So This one on the right does not have a cis trans isomer, right? This carbon has two H's. If you switch the positions of the two H's, doesn't change the structure. This one, however, has two methyls on the same side. This is the cis isomer. So what you can do is you can switch this hydrogen with that methyl and then get the trans isomer. So there are three molecules. So we have drawn the products, but now we have to circle the major product. Whoops. And don't forget to keep copying your molecule correctly. Sorry, the double bond over here doesn't react. It's still there. I almost lost half a point on each molecule. Okay, so we got the molecules drawn correctly. Which one's the major product? Well, the alkane with the most stuff hanging off of it is the major product. It's one of nature's favorites by Zaitsev rule. If you want to look up Zaitsev's rule, that's one way to spell it. There are other ways of spelling Zaitsev. Anyways, I like to circle it. Let's see, how do I get my, can I go, there we go. Let's get a different color. And maybe I'll put a box around it. The problem is that in my answer, I have to circle the major product. So maybe I'll use a box or, you know, something like this. Circle the alkene, and you'll see that I cut this bond and that bond and this bond. Ignore the hydrogen. There's 3 bonds being cut. If I circle or box this one, I only cut 1 bond. This only has 1 thing hanging off of it. It's mono substituted. This one has 3 things. That's better. It's tri-substituted. This one also is tri-substituted. I cut 1 bond, 2 bond, 3 bonds. So these are tied. And when they're tied, we say, hey, normally cis is more stable than trans. But that's only for di-substituted, right? It's crowding that makes trans more stable. So there's a methyl group next to this 2-carbon group. This one's a little less, yeah, let's just say it's tied. You break the tie. Let's change the color back. These are the major products. If you had a di-substituted alkene, then you definitely can say the trans is more stable than cis, because only in this molecule do you have 2 groups together. But in this molecule, you have these 2 groups together, and in this molecule, you have 2 groups together. So they're both kind of equally crowded. So neither one really is a clear winner here. So if it's di-substituted, trans wins over cis. But if it's tri-substituted or tetra-substituted, it's still a tie. So circle them both. They both count as the major product over this one. We're not going to see much of this being formed in the lab. Phew, that was a loaded question. Let's try the next one. It looks so weird. There's all these sulfur atoms. When do we talk about sulfur? Well, in the SN2 reaction. Okay, let's just run through the whole procedure. What degree is the halide? It's secondary, so that means any reaction of these 4 could take place. Okay, of these 2, which one's the nucleophile or base, and which one's a solvent? The more reactive compound is your nucleophile or base. This is the one that has charge, that's more reactive. All right, so what is this? Strong base, good nucleophile, weak base, weak nucleophile. Well, in our notes and in the video, we said good nucleophiles are strong bases and SN2. And the S stands for sulfur, the N stands for nitrogen. That's a good way to remembering the class of molecules that make up good nucleophiles. We have sulfur here. This turns out to be a good nucleophile. Then you might be asking, well, is it also a strong base? And the answer is no. Sulfur is not a strong base. These are both weak bases. Even when they're, well, when sulfur is negatively charged, it's a weak base. Nitrogen negatively charged is It's actually a strong base. Remember, we use this to pull the hydrogen off the end of a triple bond, and that is this hydrogen connected carbon's really a weak acid. You need a very strong base to remove it. Okay, so this is actually a weak base, which would favor E1. This is a good nucleophile favoring SN2. The other thing to remember is that E1 goes through a carbocation intermediate, just like SN1 does. So by saying it's a weak base and a good nucleophile, I'm leaning towards a good nucleophile because SN1 and E1 usually happen in the same reaction, but SN1 needs a weak nucleophile, and we don't have that. We have a good one, strong one, if you will, a strong nucleophile. So I don't see E1 and SN1 happening at the same time because your reagent needs to both be weak. This one's strong or good. So even though it's a weak base, I'm like, I don't really trust that. Here's a good tiebreaker. What the heck is this molecule? There are 4 molecules you need to have memorized, at least be able to recognize. This one is Dmso. So go back to key concepts and look up the other 3. These are aprotic solvents, polar aprotic solvent that favor SN2. And the good nucleophile is also favoring SN2. Secondary halides can do SN2. Yeah, this is an SN2 reaction. So S stands for substitute. Take away your halide and bring in the atom with the lone pair. That's a sulfur. So let's copy that molecule. And then there's a bond to the chlorine, but the chlorine's not there anymore. Now there's a sulfur atom. Wait. What happened to the sodium? What happened to these 2 carbons? Well, remember that the nucleophile is going to keep its carbons. Sulfur is making 1 ionic bond and 1 covalent bond. It likes 2 bonds. The sulfur is still making 2 bonds in the product. That's when it's stable. So just keep the carbons. The sodium's a spectator ion. After the sulfur makes a covalent bond to the carbon here, after it does a substitution, sulfur doesn't have charge anymore. It's doing its normal thing of 2 bonds. It doesn't have a charge anymore. Instead, the chlorine left as Cl minus, and that's where the sodium went. It's hanging out with the anion. That's your byproduct, and you don't have to write it because there's no carbon there. I'm just looking for this. And if that's your only product, so if you want to circle it saying, hey, my one and only product is the major product, you can. On the exam, if you didn't circle it, I'll be like, yeah, there's only one product. It must be the major product. You would get full credit. All right, 2 more here on predicting products. What the heck is this thing? It's, well, if you remember your functional groups, this is an amine. Wait, do you remember having an amine over here? That's weird. I don't know what to do with that, you might be thinking. Let's go over here. What's more reactive? Well, the one with charge. Nobody's charged over here. This is, well, this is 1-iodopropane, if you want to name it. What the heck is this? That's DMF. That favors SN2. That's one of the aprotic solvents, a polar aprotic solvent. So definitely memorize, why is that S? Definitely memorize the 4 aprotic solvents that favor SN2 because you need it here. If I recognize this is DMF, that's a big clue that we're trying to do SN2. SN2 happens between an alkyl halide, primary, secondary, or tertiary. Well, not tertiary because SN2 doesn't like crowding. Do we have a primary halide? Yeah, we do. It's right here. Okay, so this is where the organic chemist is exercising some options. You put the organic molecule on the left side, reagents here, and it turns out both this molecule and that molecule have carbons. So you can choose either one to put on the left side. So I'm just illustrating that, yeah, it doesn't always have to be alkyl halide over here. There's no rule about that. It's whatever molecule containing carbon is over here, and then your products produce molecules with carbon. That's the only thing in organic chemistry. Okay, but we'll have to realize, wait, here's my primary halide. Primary halides like to do SN2. They can also do E2. Then the N stands for nucleophile. Somebody with the lone pair, well, it's right here. It's the amine. So substitute out the iodide. So the iodide used to be connected here. Now the nitrogen is. And nitrogen, you keep your carbons, just like the sulfur did. So the ring of 4 carbons is still there. Nitrogen will kick out an H+. That'll pair up with I- and make acid. But there's no carbon there, so you don't have to draw it. And if you want to circle this, you can, but that's the only product. So you don't have to. Okay, what else we got? We got NBS followed by a second reaction. Okay, so this is multiple points. There's actually 2 reactions taking place. Definitely show your work. So if you mess up, I can at least award some partial credit. NBS H nu, darn it, it's just all about memorization. The B stands for bromine. We're going to add a bromine to this molecule somewhere. NBS prefers to attack the allylic hydrogens. It's actually a substitution reaction where hydrogen's next door to a double bond. Ooh, there's one over here too. So maybe we'll do a little mini mechanism. NBS is going to form a free radical, bromine radical, with a little light. That's H nu. The bromine radical can choose to remove a hydrogen here or a hydrogen there to form a free radical. So sometimes this free radical forms, and sometimes this free radical forms. Why? Because these are allylic radicals and they're resonance stabilized. So we also have to draw the resonance structure in our little mini mechanism. So this question did not ask for the mechanism, but it's usually a good thing to do, write out the mechanism so you can get all the possible products. Okay, so what's the resonance structure? That's where the pi bond moves towards the plus, the minus, or the radical to try and help stabilize it. So the double bond moves towards it, swings over here, and then this poor carbon used to have a double bond. It doesn't anymore, it's missing a bond. Well, it takes on the radical. And then all the other carbons are still there. Remember, in resonance structures, you cannot move atoms. You can only move electrons in resonance structures. So knowing that, I can go ahead and just draw the skeleton of the molecule, because you start with these carbons, you end up with those. All you can do is move electrons. So there's a pi bond next door to a reactive center, a radical. So move the pi bond towards it. And then the atom that's missing a double bond, ooh, this one here, that becomes the radical. There we go. We drew all our resonance structures for the first reaction. Now you add bromine to wherever the radicals are. So if you want to just go in here and add a bromine, add a bond, you can do that when you show your work. I'm not going to. I thought I would just leave it here so you could compare and contrast. There's a bromine here. Copy this molecule next. This up there. Let's see, the bromine is here. Good. And then down here, bromine is there. And then over here, bromine's over there. Okay, so that was the NBS reaction. After the NBS reaction is all done, it is, now we mix in a second set of reagents. then we wrote the word here. That's telling us it's a solvent. And ethanol ends in an OL. It reminds us there's an alcohol. And that's a protic solvent, which says no SN2. Something else will be faster. KOH, well, hopefully you recognize that from general chemistry. That's a strong base, hydroxide ion. Strong bases like to do E2. And they're good nucleophiles. They could also do SN2, but not in ethanol. The SN2 reaction gets shut down. Okay, so do E2. The E stands for make alkenes. You can also make alkynes. I can't spell. So what does that mean? Well, begin your double bond wherever the halide is. And then remember one more thing. Nature doesn't like allenes or cumulative double bonds, I think they're called. So you might think, hey, the double bond could go to the right. Theoretically, it can. So the double bond that was already there is here. Let's draw on the methyl and the ethyl. And theoretically, it could make that, but nature doesn't like this. It's not very stable. Also, this middle carbon is a pair of double bonds on either side. It's sp hybridized, and the bond angle should be 180. This is not 180 because of the ring. So it turns out, yeah, don't do that. Nature won't. She says, nope, I'm not going to make that molecule. So instead, for this molecule here, she does not make the double bond to the right. She only goes to the left. This one here, let's get a little more room. Second molecule, again, don't go to the right because then you'll get your double bonds stacked together. Nature isn't going to do that. For the second molecule, let's just draw everything there except for the bromine. Bromine is here, or was there, and now the double bond only goes to the left. Third molecule down here, let's draw everything except for the bromine. Okay, the bromine was here. It's not going to go to the right. That stacks the double bond. It could go at the end of the chain, and it could go to the left also. It could go here. Start where the halide was and go in any direction, but the nature doesn't like to stack up the double bonds. Those are the two products that result from this molecule. And then the other molecule, so I just copied this molecule, left off the bond and the bromine. And then my double bond can start here. It's not going to go down and stack up the double bonds. It can only go this way. Phew! So if you get this far, you get lots of points. But to get the last final few points, maybe 1 or 2 points, you got to circle the major products. Okay, so what do we got? Well, this double bond has 2 groups on it. This double bond has 3. So that looks pretty good. This is tri-substituted. This has 2 groups on that double bond. There's 3 groups on this one. I don't want to start circling them. Actually, I could circle one of them. So, you know, I'm just in my head circling this and seeing them cutting 3 bonds. This double bond is tri-substituted. Sorry about the banging. Got some construction going on here today. All right, both of the other, they have 1 tri-substituted, 1 di-substituted. They're tied. Down here, this is di-substituted, and this one's di-substituted. Okay, so this one loses because these 2 are better tri-substituted. This double bond's di, this one's tri, it's tied with those 3. This one, ooh, this one's tetra-substituted. Winner! This is our major product. It's also got a di-substitute, but the tetra-substitute, it's completely substituted. That's going to be your major product. Oh, I also forgot to look for cis and trans isomers, but we have a ring, right? So you can't have trans double bonds in a ring with 7 or fewer carbons. So good, we got them all. Okay. That was a big question. Oh, we got it. All right, let's do some mechanisms. Okay, step by step. The curved arrows are the most important feature. So you probably get a point or a half a point for every arrow that is correctly used. So then it's all about memorization. NBS, so yeah, the B stands for add bromine. And the S stands for, it stands for succinamide, but you could think of it as substitution. You're going to substitute out one of the hydrogens next to our double bond. That's called allylic. And unfortunately, there's 3 of them. So you need to show every product that can be produced and the mechanism for every product. So on the exam, I will try not to make it this long. You already need 3 mechanisms to represent products being formed at any one of these 3 spots. Okay, so for the sample test, I left it in here thinking, sure, there's 3 there. That gives you 3 chances at writing the mechanism. More practice, hopefully better comprehension and retention. Another exam, hopefully I'll do my best not to put such a long problem on it. Maybe there'll only be 1 site, or maybe there'll be 2. Okay, well, let's crank this out. What's the mechanism? You have to remember this is free radical. And free radicals go through an initiation step. No points earned for that word, but it helps us remember. You do get a half a point for remembering the structure of NBS. It's nitrogen with a pair of double bond O's on either side of a 5-membered ring, and the bromine's attached to the nitrogen. A little bit of light causes this bond to break. 1 line equals 2 arrows, and so 1 electron of the double bond of the single bond, 1 electron of that covalent bond moves the bromine. The other electron moves down the nitrogen. So I have to use fish hook arrows. A regular curved arrow means both electrons move. A lone pair, both of those 2 electrons move. Here, no, we're splitting the bond. 1 electron goes up, the other electron went down. In the initiation step, nitrogen forms a radical, and bromine forms a radical. Or you put the dot wherever you want. That's the initiation step. It turns out this one's really stable and doesn't react anymore. So just leave that there and move on. After initiation is propagation. Usually there's 2 steps here in propagation. Propagation steps create products. And the other pattern that's true of initiation, propagation, termination is usually a product from one previous step becomes the reagent of the next step. So the bromine radical, and I will put the dot on the side, becomes a reagent. What else is there to react with? This molecule. So let's draw that in here. Okay, and there's 3 spots. So I guess I'll just start on top. There's a hydrogen here that the bromine radical removes. So this electron will pair up with one of these electrons and connect H to Br. And then the other electron of that covalent bond, that's a single bond there, will split and just fall back on carbon. So you got a radical there. That's the first propagation step of NBS. The second propagation step is really just draw the resonance structures. So NBS is only attacking these sites because they're allylic. There are hydrogens here, and there's a hydrogen here, but those hydrogens are not reacting with NBS because you don't form stable allylic radicals. Why is allylic radicals so stable? It's because the resin is stabilized. Move the pi bond towards the radical. So redraw the skeleton because the atoms can't move in resin structures. And we move the pi bond towards the radical up here. And then who's missing a bond? This carbon is. There we go. There's the resonance. We're good. We took care of one site. let's do the propagation steps for the other ones. What's handy, let's see if I can keep that on the screen, is that these are all the curved arrows that you need. 3 curved arrows there. You don't need curved arrows among your resin structures. Another instructor might ask you to draw the resin structures using curved arrows. You can. I'm not requiring that. But what you can do, as long as you're confident you got this part right, is just kind of copy and change a little bit. We got a hydrogen down here now. So do the exact sequence of steps. The radical connects to one of these electrons. The electron makes a U-turn. You make HBr. And you make a carbon-based radical where the hydrogen used to be. And then you draw the resin structure. Pi bond, move towards the radical. And then where the double bond used to be and now it's gone, that's where the radical shows up. I do the reaction one more time. Bromine radical plus this hydrogen's allylic. So an electron here pairs up with an electron there. The other electron does a U-turn to make HBr, plus another carbon-based radical. The double bond is here, and where the hydrogen was, now there's a radical there. And then the resin structure. Drew the carbons. The atoms can't move in resin structures, only electrons. So double bond, you slide over to where the radical used to be. If you want to put the double bond this side, that's okay too. And then, hey, double bond used to be to this carbon, not anymore. That's where the radical now is. All right, we got all the propagation steps. Last thing we have to do is termination, and that's where you pair up your radicals. So for MBS, the only pairing you have to do is between a bromine radical and your carbon radicals. So put little fishhook arrows at each radical that connects them together. So there's this molecule, and where the radical used to be, I'm going to connect the bromine. If you want to angle it off to the side, you can draw a different shape, still the same molecule. Pair it up here, here. Let's see, double bonds up there. And then go down to here. Keep following the same pattern. Add a bromine radical. Maybe I'll make a long distance turn here. Let's see, the bromine's over here. I know, lots of details, huh? Excuse me. So I'm just copying the molecule, but where the dot used to be, connect a bond and a bromine. Keep going. We're almost done. Right, radical used to be here, but now bromine ends up there as a final product. Yay. Ooh, last one. Or is it? Let's see, the bromine is here now. Okay. Are these all the products? Maybe. We have to check for cis and trans isomers. Okay, so the first one, yes, this can have a cis or trans isomer. We have the methyl next to this propyl group. So we could switch these two. So the methyl is opposite the propyl group. Wait, that's this one here. This methyl is opposite the propyl. Those two are down here. So these are actually, well, you can't really call them cis and trans isomers because cis refers to the two identical groups. So these are actually E and Z isomers. It's not so important to know which one's E, which one's Z. Just know that, okay, we're good. Found all the cis trans isomers. Okay, how about this one? No, this carbon of the double bond has two H's on it. It's neither cis nor trans. Good. This one, oh, same deal. Down here at this end of the double bond has two H's, neither cis nor trans. This one, this double bond has a pair of methyls. Those are identical, neither cis nor trans. Ooh. Yeah, if you try and draw a line down here, we have all the carbons on one side, and the other for the other alkene, all the carbons are on the opposite side. That's definitely a trans isomer. If you draw on the H's, you can see that the identical hydrogens, the two identical groups, are opposite across the double bond. So we can have the other form. Let's draw this side. We got the double bond here. And now I want to put the hydrogen over here. And then the, what is that, an ethyl group? These two carbons are over there. Phew, okay, we got them all. I feel like I'm done, but if we go back and reread the question, it says circle the major products. Okay, then we will be done. So looking at all our double bonds, this one has 3 groups. This only has 2. This one has 3 groups. This one has 2. This one has 3 groups. This one only has 2. Hydrogens don't count. This only has 2. Okay, so 3 groups is the winner. Our 3 groups are here, not there, here, not there, and that one. This has 3 groups on the double bond. We have 3 major products. Phew! Want to pause the video, take a break, you deserve it. I might keep going. Okay, predicting products. Ooh, one more. How long is this gonna be? Wait, reread the question, Dennis. Oh, right, the mechanism. Sorry, we didn't have to circle. I should have reread the question. This one did not require that you circle the major products. So we just did that as a freebie. Okay, but it's a good idea to read the question. I should try and do that too, to avoid any extra work. We're doing mechanisms, and this one's a nice short one. Yay, there's a sulfur here. We've only seen sulfur in the SN2 reactions. So let's double check, make sure it's SN2, but that's my hunch. What degree is this halide? It's primary. Ooh, that favors SN2. It could also be E2. E2 doesn't care, primary, secondary, or tertiary. But SN1, E1, they make carbocations, and carbocations don't like to be primary. So SN1, E1 don't work on primary. Unless they're allylic or benzylic, then they're the carbocations resonance stabilized. No solvent given. I only have 1 molecule, so that's my reagent, the nucleophile or the base. And the K plus means the sulfur is minus. K is an alkali metal, first column. It likes to be positive 1. Making the next atom negative, ionic bond. Hey, there's a sulfur negative charge. That's a good nucleophile. Right? What are good nucleophiles? Strong bases and SN2, sulfur nitrogen 2. So sulfur, good nucleophile. And then even though sulfur is negatively charged, it's still a weak base. So SN2 is winning. E2 kind of lost here. We said there's no E1 or SN1. Yeah, it's SN2. Nice. Okay, but we want the mechanism as well as the products. So you do have to redraw this. I guess you could, as long as it's clear, you could add a bond here, but you know what? I'm just going to make sure that it's clear. And I'm going to draw in the bond to the iodide. And then I'll have the K plus and S. I need lone pairs on my nucleophile or base because that's where the curved arrow begins. You begin on electrons. Here, you begin the curved arrow on the lone pair of sulfur. And this curved arrow is saying, hey, sulfur, why don't you connect to this carbon with these 2 electrons? And when that happens, carbon says, wait, I already have 4 bonds. What's this new bond coming in here? And iodide says, no problem, I'm out of here. And steals both of these electrons, turns it into a new lone pair. And that's the mechanism. 2 curved arrows, 1 step. Beautiful. And the sulfur goes in place of the iodide. That's a substitution of the SN2 substitution. Hey, but sulfur, you keep your carbons. Well, in this case, lose the ionic bond and keep your hydrogen. We make a thiol. If you remember your functional group, the SH group is a thiol. And if you want to, the byproduct is Ki, or just leave it out. There's no carbon there. You don't have to draw it. Okay, what else do we got? Ooh, last mechanism. Okay, so don't recognize these reagents as something I had to memorize. So this is probably SN1, E1, SN2, E2. What is it? Well, what degree is your halide? Secondary, darn it. It could be anything. Which one's your reagent? Top one, it's got charge. It doesn't have to be listed on the top. It's perfectly okay and accepted if the reagents are drawn this way. So don't default say it's always on top, because it's not. Instead, look at a real reason, other than some put on top of the arrow. No, that's not a real reason. The real reason why this is a reagent, that's a solvent, is because this one's neutral, and this one's ionic. And that's more reactive. It's going to be the reagent, the reactive reagent. And it's a lone pair on this oxygen that's going to do the reacting. What's it going to do? Well, it's O with a negative charge, just like KOH was oxygen with negative charge. That was a strong base and a good nucleophile. So is this one. Lithium's in the same family as potassium. It's an alkali metal. It's a spectator ion, really. It's just balancing the negative charge on oxygen. Oxygen's the real reactive species here. It's a strong base, good nucleophile too. So as a strong base, it can do E2. As a good nucleophile, it can do SN2. Tiebreakers right here. What kind of solvent is this? It's got an OH bond. It can hydrogen bond. That makes it protic, which means, sorry, SN2, you're going to lose the race. E2 wins. SN2 is my favorite mechanism. 2 arrows, 1 step, we're done. E2 is a close second. It's 3 arrows, 1 step, and you're done. So go to the carbon adjacent to halide, pull off the hydrogen and make a double bond. Well, we don't want to stack up our double bonds. So yes, there is a hydrogen here, but nature says we're not going to stack them up. So you're not going to get a product that has a double bond on the left side. It only forms on the right. So 1 arrow, the lone pair on the oxygen as a base removes H plus. If H comes off as a plus, it didn't take any of these electrons. Instead, these electrons formed a double bond, the pi bond. And as a new bond forms here, this carbon says, whoa, I already have 4 bonds. Chlorine says, no, you don't, I'm leaving. And then the new pi bond comes in, so the carbon ends up with 4 bonds after all, and you make benzene. An aromatic compound, an arene, that's the product. Now, technically, you also change this molecule into an alcohol, and it has carbon. I'll be lenient though. So the guideline is you must draw products that contain carbon. So I would like to see this product, but I agree. The main objective is change the alkyl halide to an alkene. That's what E2 reactions do. And if you didn't draw this in, I would say, I'm predicting a problem. Sorry, predicting the products, I would say that's okay. Actually, this is a mechanism question. So in the mechanism, you actually do have to draw all your products. I probably should include this. Yeah, it's a mechanism question. So you are supposed to track all the atoms. Sorry. I'll probably forget on the exam too. If you forget this, I won't take off points. I'll kind of cringe a little bit if I don't see this in a mechanism question, but if you have this, I'll give you all the points. That's the most important thing. 3 curved arrows, 1 step, and you drew the correct product. I'm good. Oh, end of the mechanism questions. What's next? More predicting the products. Okay. Let's move this out of the way. Okay, predict the products. BR2, reacting with double bonds. Whoa, this is old. Unit 3 is about triple bonds and alkyl halides. Sorry, chemistry is a cumulative course. We're going to keep reusing old reactions. So before next exam, you do want to scroll through your list of alkene reactions from Unit 2. Yeah. Okay, so what does this do? This is old reaction. You lose the pi bond and you add 2 bromines. This is an addition reaction. So let's redraw all the carbons, right? So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And the pattern is where we had an alkene, now we have 2 halides. Also, the organic chemist doesn't balance their equations. We assume you use an excess of Br2. So unless you see a little 1 EQ, that'll tell you, no, we actually have 1-to-1 molar ratio if you see 1 EQ with your reactant. But we didn't have that here, so it's an excess. So you do have enough Br2 to react with both alkenes. So the second alkene also reacts. There we go. That's the product of the first reaction. Then take this product, it's now a reactant. True with NaNH2. Okay. It's actually an E2 reaction, but we also did talk about this reagent. It reacts with single halides to make double bonds, but it can react with a pair of halides to make triple bonds. So we're going to get a triple bond here and here by an E2 reaction. So let's draw all the carbons, 1, 2, 3, 4, 5, 6, 7. Where the halides used to be, we now have a triple bond in between them. Over here, we have a triple bond in between them. And then we have H+. Why is this acid here? Okay, this is just a little reminder that we use an excess. The NaNH2 is going to remove a hydrogen. If you want to go through the mechanism, the NaNH2 is a base, strong base, removes maybe this hydrogen first, this bromine leaves, and you get a double bond. The second molecule then, still strong base, it's going to remove this hydrogen and that bromine, make the triple bond, and then at the end of the triple bond is a hydrogen, and this is an excess, you got enough. This one, this base can pull off the hydrogen off of the end of a triple bond. So technically, at the end of this reaction with excess sodium amide, you actually have this molecule, which is a strong base. It's also a good nucleophile because you can do the extension of terminal alkyne reaction with it. We'll definitely see that in the multi-step synthesis problems. And that's what the acid is here for, to put the hydrogen back on. So this is your product. So to get full credit, at the end of this, if you see another reaction where it says add the acid, then I am looking for the anion as the product of this step. Okay, cool. Next question, right down here. Hydrogen with Lindlar's catalyst. Okay, hydrogen with palladium will attack a double bond and a triple bond, but Lindlar's catalyst only attacks the alkyne, does nothing to the alkene. So it's just a spectator also. It doesn't do anything. So it's still going to be there. But your triple bond with Lindlar's is supposed to go to a cis alkene. Okay, it's an alkene, but this is neither cis nor trans. We're done. And it's okay that this one is trans because it started trans, and alkenes do not react with Lindlar. So we're done. Cool. Even though there's an excess of hydrogen gas, there is, but Lindlar's gas doesn't react with alkenes. So no reaction at the alkene. What we got here? Ozone. Okay, we got both a double bond from the previous unit and a triple bond from this unit. Okay, ozone does a karate chop. Stop the bleeding with cotton balls. So the double bond gets cut. You cap this little half of a double bond with an O, and that actually makes formaldehyde. If you drew it like that, technically that's a skeletal drawing. I would accept that. At the other end of the double bond, you cap it with an O, you get another aldehyde. But then at the same time, the triple bond gets snapped in two, and you're supposed to cap that with an O. But then wait, HONC 1, 2, 3, 4. Oxygen prefers two bonds. It's not going to like having three. So that helps me remember, oh yeah, this is actually not the final product. You actually make a carboxylic acid. Triple bonds get cut with ozone or potassium permanganate. Triple bonds get cut to carboxylic acids. The other end though, this carbon only has one carbon. So instead of carboxylic acid, you actually make carbon dioxide. There we go. These are the three products that are made. And this was just to predict the products. Was I supposed to circle the major one? No, it didn't ask for circling the major. Good. Reading the question's a good idea. Okay, so I didn't have to circle it. I don't know why I did. Okay, I think this is the last set of questions I want to go over. And I thought I'd do all 4 sample problems. There's lessons to be learned. Yeah, that's it. There's lessons to be learned here on how to do multi-step synthesis. Okay, so what is multi-step synthesis? Well, that's what the question's asking us to do. Outline the synthesis of the following compounds. In other words, synthesize this, make it. And it's going to take more than one step. If you do it one step, that's a red flag. You're not going to earn all your points. It's going to take more than one step. Okay. The other important detail is that all the atoms of the product, how many atoms are there? There's 1, 2, 3, 4, 5, 6, 7. All 7 carbons have to originate from acetylene. Ooh, it's a word. You need to know the structure. So memorize acetylene is the simplest alkyne. Alkyne, the simplest triple bond. That's acetylene. So all 7 of these carbons had to come from the 2 carbons of acetylene or from something I call a simple alcohol. Actually, that's what my professor, when I took OChem, called them. What's a simple alcohol? Well, it's defined right here in case you forget. Simple alcohols contain 4 carbons or fewer, and they only have 1 alcohol group and nothing else. So maybe you might want to make, or you might say, hey, I wish I had this material to start with, but that's not simple. There's 2 alcohol groups. And maybe you like to have this molecule to start with. That's not simple because there's more than 4 carbons. In fact, I don't encourage you to do this, but this is the sample test, so we can waste some time here. So it's okay to do it here. So definitely don't do this during the test unless it really helps you out. But we can actually draw every simple alcohol that's allowed here. The simple alcohols have to have 4 carbons or fewer. Okay, so 1, 2, 3, 4, 1, 2, 3, 1, 2, and 1. And then they can only contain 1 OH group and no other functional groups. So I can put the alkyl group at this end or that end, but that'll be the same molecule. I can put the alcohol here or at the other end, that's the same, but we could also put it in the middle, that's different. You can put the alcohol here. You can also put it here. If you put it here, it's the same molecule. If you put it over here, it's the same molecule. But your 4 carbons could be arranged this way. And then we could put the alcohol here, or we can put it off the middle. There we go. And if you put acetylene in here, we have every molecule that it's possible to start your synthesis with. You can only use acetylene or a simple alcohol, and that's what we got. So again, just to make it clear, to get full credit, you have to make these molecules listed over here from these molecules. Okay, so that's the plan. And now you're saying, well, which one should I use? Well, that's where retrosynthetic analysis is helpful. Retrosynthetic analysis means work backwards. Okay, oh, one more detail. All your reagents, you have to make them. So things that appear over the arrow, you have to make these if they're providing carbons for your final product, right? Because we just said this molecule has to be made from these molecules. So if you draw a molecule over arrow and this molecule gives the product carbons, then this molecule has to originate from one of these. So yeah, you have to make your reagents if they're providing carbons. So the way I word it, reagents must be synthesized only if a carbon atom from the reagent ends up in the final product. Okay, so if a carbon shows up here from one of your molecules over the arrow, you have to make the molecule over the arrow. All right, let's give this a go. We need more space. Let's just start over here. Okay, work backwards. So I like drawing the molecule on the left hand, this is my right. I like drawing the molecule on the right-hand side of the page. And I think retrosynthetic analysis means, what's my last step to get here? That's pure retrosynthetic analysis. But you know what? You can also think in the forward direction, like which one of these molecules could it be useful for making this one? Okay. After you do some of these, you'll get familiar with certain clues. So let me pick out the most, one of the most important clues right now. How many carbons are here? 7. At most, how many carbons are here? 4. Okay, so one of your reactions has to make big molecules from small molecules. So that's one of the most important clues I'm reading right here. Somehow I have to connect maybe a 4 carbon group and a 3 carbon group to equal 7. So that's where we start thinking retrosynthetically. How can we make this molecule from small molecules? Or more to the point, what reactions do we have or do we know that make big molecules? I think there are 3. I think 3 reactions we've done that take small molecules and make bigger molecules. One is the extension of terminal alkynes. So if you have a triple bond, true with sodium amide, to make a negatively charged anion, and then bring in either a methyl or a primary halide. Doesn't work if it's secondary, doesn't work if it's tertiary. So maybe I'll just bring in a methyl, and you pick your halide. Bromine's my favorite. And then actually it's an SN2 reaction. Lone pair on the triple bond kicks out the bromine, and where there used to be 2 carbons in one, now you have a 3 carbon molecule. It's a bigger molecule. Extension of terminal alkyne reaction. Another one is the Gilman reaction, or the Corey-House reaction, or the Cooley reaction, however you want to call it. This one starts with, well, it can be any alkyl halide, so maybe it's tertiary. You add lithium first to make the lithium compound. You then add copper iodide, CuI, to make the Cooley reagent. So wherever the lithium was, you then connect CuLi, Cooley. I know, it's silly little joke there, or a way to remember it. And then you have to add a methyl or a primary halide. Technically, you could use a vinyl or an aryl. They work too. I don't think it'll be useful to you on this exam. So maybe we'll use the same one. Let's use methyl bromide. And then wherever the copper was, that's where the carbons add. So the carbon which has the bromine now, let's do it this. Ooh, that's secondary. Can't do secondary. Let's put the bromine over here. And then maybe over here, there's a chain. Yeah, let's do that. Okay, so even though this is not primary, doesn't matter. The halide is primary. Wherever the halide is, that's the point of connection where you attach, you substitute. Where the copper is, you now put the carbon. So grab these carbons, and then it was going to connect to the copper, but now it connects to this carbon. And there's 1, 2, 3, 1, 2, 3, and then there's a branch. And that's your product. Third reaction is the Suzuki Miyura reaction. And that's where you take an aryl or a vinyl boronic acid and you react it with some aryl or vinyl halide, and then you have to use that triphenylphosphine catalyst. Oh my goodness, do I remember this one? Hope so. There we go, with a little copper carbonate, maybe THF. I think that's optional on the exam. And I'll connect your two benzene rings together. They get connected where the boron and the halide are currently connected. That one's not going to be so useful because you always have to start with benzene rings or double bonds, alkenes, and this is synthesis. You'll have to make these. And we don't know how to put a boron on a benzene ring yet. So not useful in synthesis problems, at least not in this level of organic chemistry. It turns out that's really powerful, very useful in the real world for making molecules. That's why it was one of our reactions we studied. But here in, what is this, sophomore level organic chemistry, college level organic chemistry, this particular reaction is not useful. So we're left with two. These are two ways to make big molecules, and they both work. So trick here, let's do the Gilman first. That's kind of nice that this molecule is looking kind of similar to this one. So one way to analyze this and try to figure it out is if this is your product, but let's pretend this is your product. How did you know to start with this molecule? Well, these 4 carbons are right here. Yeah, let's do that one. And then how'd you know to bring in this molecule here? Well, because these carbons match those carbons. That's not a mechanism curved arrow. Let's just say, hey, they match. So do the same thing here. This has 7 carbons, so let's break it up into a group of 3 and a group of 4. May I switch colors again? I'm terrible with colors. Did you know I'm partially colorblind? So if I don't have the same colors, sorry, my bad. But at least they're different. Okay, so now we have choices. Do you want to begin with this molecule with the halide? And then near the end, put this group on? Or do you want to do the reverse? Do you want to end with this one? And the correct answer is you have to end with the primary halide. So this carbon's primary, but this one's secondary. So you have to start with this one. So we're going to start with these 3 carbons, and we're going to do the Gilman. So I start with 3 carbons, not 4. Pick your favorite halide. I'm going with bromine. Treat it with lithium. If you don't want to draw this, you don't have to. Synthesis is all about showing the reagents and the starting material. So you can skip drawing that if you want and just say, hey, first reaction, add lithium. Second reaction, add copper iodide. And then third reaction, well, I do want to draw this, but you don't have to. I'm sorry, you don't have to draw this product. I was thinking about doing it and I realized, I don't want to. But if you want to, you can. Maybe I should. So what do we got? We got these. They used to connect the bromine. Now it connects the coulee. And there's 2 of them. And then finally, the last step, bring in this group. No, bring in this group. And our point of connection is where halide is. And yay, it's primary, so this should work. And that does it. Just make this a real long arrow because the reaction between these 2 molecules makes that one. Yay, I'm done. Get my test back. I lost 2 points. Why? Because this molecule has to come from acetylene or simple alcohols. Darn it. Okay, so we're not done yet. We got a lot of partial credit. Hey, got a lot of partial credit. Let go. There we go. Okay. But now I need to go back. There we go. Okay, good. Okay, so scroll down a little bit. We need more room. This molecule needs to come from, man, this better work, one of these molecules. And if you stare a little while, we got 3 carbons with a group off the middle, and we have 3 carbons with a group off the middle. Yeah. So let's start with this molecule and change it into that one. How do you take an alcohol and make it into a halide? HBr, if this was tertiary, but use PBr3. Okay. Most of our starting materials are all alcohols. So, oh my goodness, you're going to be using PBr3 all the time because it'll be very helpful to change the alcohol group to a halide because Unit 3 is about reactions of alkyl halides. So PBr3 is your friend. And if you don't like bromine, if you got a beef on bromine, that's fine. Switch over and do chlorine. Start with an alcohol. Add SOCl2, that's your friend. And now you start with the chlorine. And then you can treat it with lithium, copper iodide, and that molecule with the chlorine. Doesn't matter, your favorite halide, whatever it might be, and that'll make the product, right? 1, 2, 3, 4, 5, 6, and 7. Yeah, that's the molecule. Okay, so we got more partial credit, yay! So now these 3 carbons come from a legal starting material. It's a simple alcohol, 4 carbons or fewer, only 1 alcohol group. Yeah, these 3 carbons made or provided for these 3 carbons, but what about those 4 carbons? They have to come from here. So what you can do is say, well, how about where the chlorine used to be, or chlorine is currently, that's where the alcohol used to be. How do you change an alcohol to a chlorine? SOCl2. If you want to use the bromine, then again, start with the alcohol and use PBr3. And if you want to just do this, just write arrows across your page like I did, that is fine. I can read that and say, hey, you get full credit now because all these reactions work and all 7 carbons come from an alcohol of 4 carbons or fewer. So here's 3 carbons, here's another 4, gives me 7. These all these reactions will connect them correctly and make that molecule. Nice. Okay, this video is going long. I had intended to go through and show you how this set of reactions can work, but maybe we'll use this set of reactions on the next problem. What is the next problem? There it is. Let's make this molecule over here. Let's get some blank space. How many carbons were there? 5? Yeah, double bonds alternating. Okay. So we're going to try and make this molecule. Double bond and another double bond. And if you want to put the double bond on either side of the line, it doesn't matter. Okay, this molecule has 5 carbons. And the most we have available to us are 4-carbon simple alcohols. So we need a reaction that connects 2 together. Now the Gilman reaction, let's go back and view that. That usually, oh, it's up here. That only makes, or usually only makes alkanes. So the product is an alkane. The product is an alkane, and that's boring. We don't have many reactions that change alkanes into other functional groups. But the other way to make big molecules is by the extension of terminal alkynes, and the products will have an alkyne. And we have reactions. We have all kinds of reactions that react with alkynes. Sorry, that was, yeah, the video is too long for bad puns. That's the reaction you want to use. We do know how to change a triple bond into a double bond. So one of these double bonds was used, it used to be a triple bond. Okay, so here's an approach you might take, and I want to just show it to you because it turns out to be wrong, but you don't know that from this onset. You might say, okay, I'm working backwards. I'm going to pick, oh, let's pick the first. Whoops, that's 6 carbons. Let's pick the first one to be a triple bond. And you might say, okay, how did you take this triple bond and make it a double bond? Maybe use hydrogen gas and Lindlar's catalyst. Or you could have used sodium and ammonia. Or that's, you know, that makes a trans double bond. Or you could have used lithium and ammonia. You don't have to write all the reagents. One will do. I picked hydrogen and Lindlar catalyst. And then you might say, okay, I connected these together by taking the anion of the triple bond, and then I connected it. Well, there's 2 carbons here, 1, 2. So the rest of them, 3, with the double bond, used to have my halide. Let's redraw that so it's a little more clear. Double bond, halide. And I'm saying, okay, triple bond, do an SN2 reaction, bump out this halide to make that. And the answer is no can do. This is a vinyl halide. Alkyl halides are sp3. They're alkanes connected to bromine. This is an alkene. It doesn't work. So you're going to lose major points here. I give you some partial credit for saying, well, I see your logic, but this reaction doesn't work. The extension of terminal alkyne reactions requires the last step be methyl or primary alkyl halide. I should have said primary alkyl halide, which means it comes from an alkane. Okay, so that's not going to work. Then you might say, well, then why don't we start with the other part being a triple bond? Instead of the first double bond being a triple bond, well, then the problem is still going to happen. You're going to say, well, then this anion, these 3 carbons, 1, 2, 3 with a triple bond, try and connect to this. And darn it, it's still vinyl, the nickname for a bromine on an alkene. That's not going to work either. Okay, so what we want to do instead is take away that pi bond. So we thought backwards, retrosynthetic analysis. We got to here and hit a roadblock. But we can use that information and say, well, okay, wait a minute. What if I start, or somewhere in during my synthesis, I have this molecule reacting with this one, but I don't have a double bond there. Well, this now will work. This is a primary alkyl halide. That works fine. And then you connect 2 carbons plus 3 carbons equals 5 carbons. Good, because that's what we want. Now we need to change this molecule into that one. Retrosynthetic analysis, help me out. Okay, I need a double bond where there's a single bond. And I don't have a reaction that changes single bonds into double. I don't. Or do I? What reactions do that? Well, we talked about the E2 reaction. And before E2, we talked about how to make alkenes. You can take this single bond, treat it with a strong base, maybe add a protic solvent, and you can get an E2 reaction. You can make an alkene that way. Ooh, that's a great idea. Let's do that. Let's say we're trying to get, there's scroll over a little bit. Here's our product. Let me redraw this molecule down here. So there it is. And we could have said, well, I need a double bond right here. That's this one. So in the last step, let's say I did not have the double bond yet. Instead, let's put a halide here and react it with NaNH2. And sure, the double bond can go to the right sometimes, but it can also go to the left. And for synthesis, as long as one of your 2 products, or if maybe it's a reaction that makes 5 products, as long as one of them is what you want, you're good. And you don't have to draw the other one. So I'm putting in parentheses because you don't have to draw it, right? So when this molecule reacts with this molecule, it makes both of these and the cis, darn it. You also make the cis isomer here. But I don't care about the extras. I only want to make this molecule. So that's all you have to write. Okay, so working backwards, that's a good last step. Now, is there a way that I can get from this molecule to this one? I don't see a good way, but let's start working in that direction. We got a triple bond here. How do we make it a double bond? Well, you got the reactions right up here. Use hydrogen gas and Lindlar's. This is neither cis nor trans, so that'll work. Or use one of these. I'll use one of those this time. Sorry, NH3. So now this is a double bond. And then the bromine is 2 carbons away from the end of a double bond. Darn it, if it was only 1 carbon away from the double bond, that's allylic. And you can use NBS to make it. Right, so you have a double bond and the carbon next to it, if it has a hydrogen, it can substitute with the B of bromine, put the bromine right there. And then it turns out if your bromine is right here, the double bond could go left, but it's not going to stack up, or it could go right, and that's what we want. Yay! Major points earned here. Do we get all the points? Well, 5 carbons come from these 5, come from those 5, those 5. Ooh, they come from 2 carbons and 3 carbons. Are these legal starting materials? Are they acetylene or alcohols of 4 carbons or fewer? No. That one almost looks like acetylene. So let's start with acetylene. There we go. If you take acetylene, that's legal. You can start with this. You don't have to make it. You can start with that one. Treat with this strong base. You can make this. Good. Now I just have to figure out how to make this molecule. Well, there's 3 carbons with a bromine at the end. So why don't we start with 3 carbons and an alcohol at the end? How do you change the alcohol to bromine? PBr3. And we are done and full credit. Start with these 3 carbons on a simple alcohol, 4 carbons or fewer, and acetylene. And we piece it all together to make the final product. Nice. Cool. All righty, let's see, what else do we got? Got a couple more. Okay. Retrosynthetic analysis, we got an ether here and an alkene. Okay, so thinking backwards, well, we already know about how to make double bonds. They can be made from a triple bond, like down here in Lindlar Callus or whatever. You can also make a double bond by, where is it? Oh, it's right there. A halide and a strong base. Alkyl halide strong base can make a double bond. So those are the 2 good ways of making double bonds. So maybe we can do that. Hey, wait a second. Double bond and a halide. Double bond and an ether. This is allylic. We might use that. Okay, so focusing on the alkane, there's 2 ways of making it, from a triple bond or from an alkyl halide. How do you make an ether? There's only one way we've seen so far, and that's by an SN2 reaction. If you take the anion of an alcohol and a primary or secondary or a methyl halide, you can do an SN2 reaction. Can't be tertiary, right? Too bulky. Lone pair on the negative oxygen bumps out the halide, and then the oxygen keeps its carbons and connects to the other carbon where the halide was attached. Hey, that's an ether. And that's what we got here too. I like that. Let's do that as our final step. Let's make this bond, which is that bond. So the new bond was made when this group used to have a bromine, and this group was attached to oxygen. Okay, so let's have this group attached to a bromine. So I got 1, 2, 3, 4, 1, 2, 3, 4 carbons, and where the oxygen is attached, that's where it used to be a bromine. And then these 3 carbons, they can be attached to the negatively charged oxygen. And then this is a primary halide. This will enjoy doing SN2. You want to add a little Dmso? I'll smile if I see that on the multi-step synthesis. That's telling me, yes, you're trying to do SN2. You're using a aprotic solvent. You can use DMF, acetone, or acetonitrile, one of the 4 solvents for SN2. That'll work. Yay! Awesome. Lots of points there. Okay, but these are not legal starting materials. We're 1 reaction away from this one being an alcohol. Okay, simple alcohol with 3 carbons, that's legal. So how do you remove a hydrogen to form an anion? How do you remove H plus with a strong base? So what strong bases do you know? How about sodium hydroxide? No. Sodium hydroxide is going to make water, and then this base. This is a strong base. It's going to react with the water to make hydroxide ion, this alcohol. It's an equilibrium reaction. You're starting with O minus, you're ending with O minus. It's an equilibrium. You need a stronger base. So try using sodium amide. Yeah. Remember how we talked about for the extension of terminal alkyne reactions, you had to use not sodium hydroxide, but sodium amide, because hydroxide ion was not a strong enough base, remove the hydrogen off the end of a carbon. Sodium hydroxide can remove this hydrogen, but it's set up as an equilibrium, not a complete reaction. So use a stronger base to get the job done. Cool. All right, so we got major points there. Oh, I know. Video's going way too long, but we only have this one and one more to finish up. So let's keep going. Okay, so we start with the alcohol, legal starting material, made this, react with that, made that, good. There's 4 carbons here and 3 more, so all 7. Well, 3 of them came from a legal starting material. The other 4 comes from here. Ooh, I need to make that. If you think about starting with the alcohol, let's do the wrong way. You might say, okay, how about if I start with this and add PBr3? And I can make that. That's true, that works. But now you have to make this thing. And you might say, well, no problem. Let's start out with this and treat it with strong base. Because Dennis, strong bases react with alkyl halides to make double bonds. Yeah, that's true. But strong bases react with alcohols too. And actually it reacts faster. So this strong base is not going to go after that hydrogen. It's going to go after this one. Dang it. Okay, that's not a good route. So sorry about that. Instead, go back and say, well, what kind of halide is this? It's allylic. So let me rewrite it down here because I got a big mess there. If it's allylic, make the halide from NBS. So start with this alkene. There's an allylic hydrogen that can substitute with the bromine. Nice, that's so much better. And then now you can make this alkene with the strong base and an alkyl halide. That works just fine. Yeah, I know the double bond can also be formed on the left side. You also get the cis. Who cares? As long as one of the products is the one you want, full credit for the synthesis problem. And then finally, we have to start with a 4-carbon alcohol, this one, and use PBr3. Nice. Okay, so that's how you do that problem. Let's do this last one. This one shouldn't be as long. I keep cringing when I look at this because there's a mistake. So I'll try and catch it when I write the exam. I keep leaving it in here so I can point out this problem on a real exam. And if it happens to you, send me an email after the exam and I'll award more points if I make the same mistake again. What's the mistake? Well, what's your very last step? Let's do retrosynthetic analysis. Well, this is an alkane, pure alkane. The only thing special is that the hydrogens are trans to the ring. Oh, cyclopropane. Ooh, back in Unit 2, we knew how to make cyclopropane. There was a reaction that had 2 chlorines on one carbon of the triangle, but there's another one, copper zinc, right? That said it could take a double bond. They put the right spot. Yeah, and it's trans, good. You can start with an alkene and turn it into a cyclopropane ring. Sweet. Okay, and then now you have to make this molecule. So you know what? This has more than 4 carbons. So we need a reaction to connect 2 small molecules together. And that's either the Gilman reaction or the extension of terminal alkynes. So we need an alkyne here. So you change the alkyne to this and keep it trans. We definitely have to use either the sodium or the lithium and ammonia reaction to get to trans alkene. So now I need to make this. Well, you could have made it from, let's see. If I connect this bond, then I have 4 carbons and 3. If I try to connect this bond, if I say, hey, why don't we make this molecule? Well, this one has 5 carbons in it. It's going to take more work. So don't do it that way. Cut it the other way. So take these 4 carbons with the triple bond on the left side, connect it to 3 carbons. And what we want to do is connect these 2 carbons together. This one used to be an anion, and this one used to have your favorite halide on it. This molecule can be made from the alcohol again with PBr3. This one is made from the normal triple bond with NaNH2. That pulls a hydrogen off the end to make this. This is not a legal starting material, so you can do this reaction again, right? You can do extension of terminal alkyne. That works. You can do that again. You could say, why don't we connect this and this? Totally works. Another idea, if you want to be creative, is say, well, how about we start with a pair of halides here instead? Treat that with base 2. That makes a triple bond 2. So you can decide to do it either way. This one came from Br2 and an alkene. The alkene came from maybe the alkyl halide. We put the halide here. Oh, don't put the halide there. Yeah, you put the halide there, sure. With a strong base again. And then the alcohol used to be there. PBr3. That works, 4 carbons, we're good. Or you could have done it this way. This could have been the alcohol, PBr3, triple bond, NaNH2. So you don't have to show both routes. I'm just saying that in multi-step synthesis, there's more than one correct answer. So if you get stuck doing it this way, see if there's another way you can do it. Don't have to do it my way. There's lots of correct answers. Why did I choose this one? Why do I cringe? Okay, let's make sure we get all our points. How many carbons are here? I got 1, 2, 3, 4, 5, 6, 7, plus the triangles, 8 carbons. This one has 1, 2, 3, 4, 5, 6, 7. Oh, here's the 8th carbon. We still have to make that. We do. And I have no reaction to do that. How do you put iodide on a ring? Well, if you start with methyl alcohol, no, that doesn't work. If you start with a tertiary alcohol, you could use HI. We did talk about that working. But if you have methanol and you add HI, you're not going to get a reaction. This goes through a carbocation intermediate. That's why it needs to be tertiary. And methyl carbocations are so unstable, this is going to not react. And you need 2 of them. So yeah, we don't have a way. So here was my mistake as a teacher. The requirement is you're supposed to make all the compounds that contribute carbons. They have to come from alcohols of 4 carbons or fewer or acetylene. And so this is an out of bounds problem. Okay, so I'm not going to ask you to make this on the exam because we don't have a method to make that. There are reactions that exist. We just haven't discussed them yet. Great. Am I really ending this video on a problem? I think I am. It's long enough. Good luck on your exam.